Alright. Next, I want to show you what is called the parallel access theorem. Again, this is a topic which you have been exposed to earlier also. However, not completely. You must be knowing a part of parallel access theorem, which we will cover in this class also. But then there is something additional which might be new to you. But before I go to the parallel access theorem, I want to clarify that on some of the slides, you may not see this double bar appearing here. So earlier I said that this is how what I call as the inertia matrix of RB at A relative to coordinate system right. Earlier I was putting double bars here. Now onwards I may omit, I may not write that, but it is just for convenience. It is implied there, it still has meaning, but just for convenience I may leave that double bar at some places. Okay, parallel access theorem. So before I present to you the full form of the parallel access theorem, let's prepare some background. We have an RB here. We have this RBM shown with this red outline. A is a point fixed to RB, and C it is the center of mass of the RB. Now we are going to put two different Cartesian coordinate systems. The first Cartesian coordinate system is what I have here. A x1 e1, x2 e2, x3 e3. A is the origin of the coordinate system. So clearly this coordinate system has its origin fixed at point A, and then it has three axes which are parallel to E1 hat, E2 hat and E3 hat. Right? And if there is any point P in the first coordinate system, its coordinates will be x1, x2, x3. That's what is meant by the three letters that I am writing here. This is my first Cartesian coordinate system. I am going to put another Cartesian coordinate system, and that Cartesian coordinate system will have its origin at the center of mass. This is the green color coordinate system. It has its origin at C. Now the three unit vectors associated with the green coordinate system are the same three unit vectors what I had here in the blue coordinate system. The unit vectors are the same. However, since the origins are different, I must make a distinction between x1 here and x1 here. And that distinction I am making by putting an over bar here. Essentially what I am saying is that in the second coordinate system, the same point P will have its coordinates as x1 bar, x2 bar and x3 bar. Now these are just a scalar. Do not confuse this as a vector. It is just a scalar. I am putting an over bar just to distinguish it from this x1 that is appearing here. Okay. Same point P, x1, x2, x3, coordinates of the point in this blue coordinate system. Same point P, coordinates are x1 bar, x2 bar, x3 bar when your working coordinate system becomes the green coordinate system. Okay. Now, if we take P as a typical point on the RB, look at this diagram and ensure that you understand or you are convinced that I can write the vector RPC, RPC, C is here, P is here, RPC as this, x1 bar E1, x2 bar E2, x3 bar E3. And the vector RPA, if I have to express, I can write it as x1 E1, x2 E2 and x3 E3. Okay. Now if I want to write the vector RCA, look at the figure, RCA, vector going from the origin of the blue coordinate system to the origin of the green coordinate system. That vector will be represented as xc1, xc2 and xc3, where xc1, xc2, xc3 are the coordinates of center of mass relative to the coordinate system, this one. Okay, so C has these are the coordinates of point C, measured from which coordinate system? The blue coordinate system. What will be the coordinates of C measured from the green coordinate system? That will be simply 0, 0, 0. Right? Point C, listen to me again. Point C will have its coordinates measured from the green coordinate system as 0, 0, 0. Why? Because C is the origin of the green coordinate system. But if I try to write the coordinates of C measured from the blue coordinate system, it will in general be not 0, 0, 0. It will be something, and that something I am saying is xc1, xc2 and xc3. These are the coordinates of C. So C stands for center of mass, okay, and 1, 2, 3 stand for the first, second and third coordinates. Alright. Now let IA represent inertia matrix of RB at A relative to this coordinate system, the green coordinate system. And let IC represent the inertia matrix of RB at C relative to the blue, this is the blue coordinate system. I mentioned it as green. Whenever the origin is A, it is green, it's the blue coordinate system. Whenever the origin is C, it is the green coordinate system. Okay. So it is the same RB, but I am talking about inertia matrix at two different points. Not only at two different points, I am also talking about inertia matrix relative to two different coordinate systems. Okay, so IA and IC are such matrices. Now the parallel axis theorem states that, so I am giving you the full form of the parallel axis theorem up front, and I want to explain this first and then I will show you the proof. The parallel axis theorem has 6 things to tell us. It is a set of 6 statements. 6 statements. First statement, IA11 is equal to IC11 plus m times xc2 square plus xc3 square. What is m? M is the total mass of the RB. What it is essentially telling us, it is telling us that if you know the inertia matrix components of the RB at point C, it is possible to calculate the inertia matrix, components of inertia matrix of the same RB at another point A. You can go from center of mass to another point A. Okay, that is the relationship. xc2 is the xc2 and xc3 are the coordinates of center of mass measured from the blue coordinate system. Understand this. Understand what it is trying to do. Now, if you understand what it is trying to do, then you can go to the next statement, and then it's just a matter of changing indices. So the first was about 1,1 component, going from IC11 to IA11. Second is about going from IC22 to IA22. And the third is IC33 to IA33. And here there is a very clear pattern in which these indices change. Here it was 2, 3. When you are talking about 1, 1, this is 2 and 3. When you are talking about 2, 2, 2 becomes 3, 3 becomes 1. So it's actually cyclic. You have 1, 2, 3. Goes like this. So here you had 2. So from 2 I go to 3. So 2 becomes 3. Here I had 3. According to this cycle, 3 should become 1. Indeed, 3 is becoming 1. Here it goes from 3 to 1 and 1 to 2. So these are the first three statements relating moments of inertia at point C and at point A. There are three more statements which relate products of inertia. And this is what I believe is a new thing. These first three statements are covered in 11th and 12th also classes. But these three statements are new. They are new because the concept of products of inertia itself is new. Now let's see the relationships here. First one is taking us from IC12 to IA12. And as it takes us from IC12 to IA12, you have an extra term here which is minus times m total mass multiplied by the first coordinates of the center of mass and the second coordinate of the center of mass measured from the blue coordinate system. So here you have indices 1, 2, 1, 2, and then it is 1 and 2. Okay. Then you have IC23 going to IA23 and IC31 going to IA31. And the additional terms like this. Very useful theorem. Very useful theorem. How is it useful? Suppose you know IC11 and you want to go to IA11, you do not have to perform all that integration over and over again. What integration I'm talking about? IA11 by definition is this. You have to perform this integral to get IA11. But if you know IC11, then you just have to add this extra term which is not an integration. Not an integration. You can readily find this. And thus, you can avoid computing this integral over and over again. That is the utility of this theorem. Okay. You have to keep in mind before you apply this that you must go from center of mass to another point A. If C is not the center of mass, this theorem will not hold good. C has to be the center of mass. Always from center of mass to any arbitrary point on the RB. Not from one arbitrary point on the RB to another point on another arbitrary point on RB. Not like that. That's number one constraint. The number two constraint is that when I say IC11, the three axes are still parallel to the same three axes of the blue coordinate system. The green and the blue coordinate system must have their axes parallel to each other correspondingly, 1, 1, 2, 2 and 3, 3, and thus the name parallel axis theorem. Keep these in mind. We will prove it. Okay. Now before I prove the statements per se, before I prove these statements, let's have a useful relationship with us. I mean, let's have a useful formula with us. And that is this, what I have written here. Whenever I come across this integral RPCdm, we can set that to be 0. It is always true. Where P is a typical point on the RB and C is the center of mass. Let me first prove this. So the left hand side can be written as, RPC can be written as RPO minus RCO dm. Right? You can look at this. So O is a point here, any point in space you can take. RPC can be written as RPO, which is this vector, and then you have another vector RCO. RPO, RC. You can write it as RPO minus RCO dm. So I've started with the left hand side. I'll prove that it is 0. Now RPO dm, if you recall, that is the definition of center of mass. This is how center of mass is defined. Now in this integration, RCO is a constant. I pull that out, and indeed it becomes m times RCO minus m times RCO. So this is 0. Okay. Now if I use the green coordinate system as my working coordinate system, green coordinate system. What was the green coordinate system? This was, look at the green coordinate system. Okay. The coordinate system which is fixed, which has its origin at C. If I use that coordinate system, RPC can be written as, P is a typical point, right? So RPC can be written as x1 bar E1, x2 bar E2, x3 bar E3. Right? P is a typical point that will have its scale, the RPC vector will have these components. Now if RPC dm integral is 0, what I just proved, then it implies what? It implies This whole thing should be 0. But then E1, E2 and E3 are not depending on this integration. E1, E2, E3 are independent of the integration process, and thus this equation should give me this. And since E1, E2 and E3 are mutually perpendicular unit vectors, I effectively get three equations. x1 dm integral 0, x2 dm integral 0, and x3 dm integral 0. Over the whole body. We will use these three relationships while trying to prove the parallel axis theorem. Okay. Now it's the same two coordinate systems. Since I have black background on the screen, I did not use green and blue. So this yellow is actually the blue coordinate system, and this white is the one which I was showing as the green coordinate system earlier. Now, with all these points A, C, and P, I will first write this equation. Let's call it 1. RPA. I will not draw the vectors here. It's already quite busy, this diagram, but I hope you will be able to visualize. RPA, vector going from A to P, is equal to RCA plus RPC. Okay. Now RPA I am going to write as x1 E1, x2 E2, x3 E3. I am going to write RCA as RCA vector. I am going to write as xC1 E1, xC2 E2, xC3 E3. Let's call it second equation. And then finally RPC. RPC, how can I write it? I can write it as x1 E1, x2 E2, x3 E3. Okay, let's call it 3. And this was, let's call it 4. If you substitute 2, 3 and 4 in 1, I can extract 3 scalar equations out of that, and those 3 scalar equations would be this. I'm skipping a few steps, but it's not difficult. You just have to substitute and match the coefficients of E1 on both sides. That will give you this. Match the coefficients of E2 on both sides. That gives us this. Match the coefficients of E3 on both sides. You get this. Now let me write IA11. IA11 by definition is this. I am going to use 6 and 7 in this star and make it appear more complicated. Algebra wise, it will start looking more complicated. It will look like this. This is what it will become. Right? Now let's expand the square terms on the right hand side. A plus b whole square will be equal to a square plus b square plus twice ab. Using that formula, let's expand both the square terms on the left hand side, or on the right hand side. You get a bunch of terms. So all these three terms come from the first term here. And then three more terms, that would be x3 bar square dm, xc3 square dm plus 2x3 bar xc3 dm. I'm going to club some terms, various terms under different groups. I'm going to take this term and put them together. Okay. Now here you see this xc2 square dm is a constant during the integration process. xc2 has nothing to do with the typical point P in the neighborhood of which we are considering the mass dm. And thus xc2 can be pulled out of the integration and this becomes xc2 square dm. Similarly, this term xc3 square is constant for integration. Same thing applies here. At least xc2 from here can be pulled out of the integration. And of course 2 I will pull out. So I am left with x2 dm. x3 dm. I'll write here xc2, xc3 constants. Process. Now these two terms are Nothing. They add up. I mean, by definition, this whole thing can be written as IC11. That is what IC11 should be by definition of the moment of inertia 1-1 component. This is what IC11 is. This integration will simply give you M, and same, this will give you M. So it means this I can write as mxc2 square mxc3 square. Now look at this term. What is the fate of this term? Go back 2 slides before. What I said. Integral of x1 dm0, integral x1 bar dm0, integral of x2 bar dm0, integral of x3 bar dm0. We have already shown that. And that's why this is 0 and so is this term 0. What do we get? We get IA11 from here. That equals 3 terms. First is IC11 and then mxc2 square plus xc3 square. This is the first statement of the parallel access theorem. Slide number 15, 16. This is what I claimed was the first statement. I have proved it. Okay. Since I have already shown the proof of 1-1, I really don't have to repeat the process for 2-2 and 3-3. Very similar steps. I'm just leaving it here, saying that this could as well be proved following the same approach. Like to write it as 2, like to write that as 3 becomes 1, 2 becomes 3, 3 becomes 1. Okay, and this will be xc1 square mxc2 square. Similar proofs. Leaving it, not repeating the steps. Instead, I would pick up one of these, the other 3 statements, which is here, and would like to prove this. IA12 equals this. Let's quickly have the proof of this. Proof of IA12 C12 minus XC2. Even for this, steps are very similar. I start with IA12, which by definition is this. Replace x1 by get 4 terms. Four terms. XC2 xc1, xc2. We recognize that this term is indeed plus IC12 by definition. Fate of second term, xc2 taken as a common factor, x1 dm, which will now become 0. xc1 taken as a common factor, x2 dm will now become 0. And then the last term, both xc1 and xc2 are constant. They will be pulled out of the integration, leaving an integral dm, which can be replaced by m times xc1 xc2, which is equal to RHS of this double stuff. We have proved this also. Similarly, you can prove the other two relationships for the product of inertia. Okay. Okay. Now on this slide, I am showing how the inertia matrix of an RB can be computed by adding the inertia matrix of subparts of an RB. This is something like the center of mass concept we discussed earlier. If your RB can be recognized, or if your RB is comprised of smaller subparts, and you know the centers of mass, you know the locations of the centers of mass of those individual parts, you can assemble things together and find the center of mass of the entire RB. That composite RB, which is comprised of smaller subparts. Similar concept is here for the inertia matrix. You have a composite RB, which I am showing here in this faded blue color. So the composite RB is comprised of what? It is comprised of a cuboid, which I am trying to outline now. It's a cuboid. I am calling that as RB2. And then on that cuboid there is a cylindrical part welded. Okay, I am calling that as RB1. And then on the other end there is another cylindrical part welded. I'm calling it as RB3. So this combination of 1, 2, 3 I am calling as a composite RB. Composite RB. And on that composite RB there is a point A which is fixed on this composite RB. And then you have also been given a coordinate system, your working coordinate system, x1, e1, x2, e2, x3, e3. And you are being asked to find the inertia matrix of the composite body at point A relative to the coordinate system shown here. So you can do this computation in parts, like what I have shown on the right hand side of the slide. So the inertia matrix of the composite body can be written in this manner, what I have on the right hand side. 3 parts. IA, and then I have added another superscript on the left hand side. IA1. Okay, this is not I, this is Roman 1, this is Roman 1, this is Roman 2, and this is Roman 3. So you have IA of part 1, IA of part 2 and IA of part 3. If you add them together, you will get IA of the whole composite body. This can also be proved easily. Not showing you the proof, but by going back to the definition of various components of inertia matrix, you can show that this IA can be computed in 3 parts. Okay. Now, once you have written this expression as 3 parts, then you go to the individual parts. Like I go to IA1. So this is the RB1, this cylinder. And what we have to do now is use known components of inertia matrix of an individual RB, in this case 1, at its own center of mass. It may be known already. For regular shapes, cuboid, cylinder, circular disc, sphere, hemisphere, all these regular shapes, for these regular shapes, we compute the expressions. We find the expressions for the inertia components using integration and then put it in some table, in some reference book. Just like center of mass. Find the expression once by doing integration. Keep it as a reference data, as a reference information. I will show such tables maybe in the next class. So for regular shapes, you already know IA1. You will know I of 1 at its own center of mass. You will know it at its own center of mass. And what I am trying to say here is that if you know the inertia components of this RB at its center of mass, you can use parallel access theorem and find the inertia component of this RB at A. You can move from the center of mass here to A, and that is what this is. Next you go to body number 2. If A is its own center of mass already, then you already know IA2. You go to the third body, it has its center of mass here. From a table you find IC3 and then use parallel access theorem to get IA3. Then add everything together, you will get IA. It can be done like this. I have a couple of questions on set 5 and that would help you grasp this idea better. Sometimes we have an RB, composite RB, in which one of the parts seem to be missing, like this RB. This composite RB, I am recognizing that there are 3 parts. One is the sort of cuboid here. Second is the cylinder, and third cylinder is missing. It is hollow. Just like center of mass. When we were trying to find center of mass, we said that if there is a missing part, you can put a minus sign and handle that kind of scenario. Same is the situation here. If you have a missing part and you want to find IA of the whole composite body, it will be IA of Roman 1, IA of Roman 2 minus IA of Roman 3. This is how we can compute IA quickly. Again, there is underlying proof for all. I am not going over that, but if you are curious, you can prove it and then use. But the bottom line is these formulations will be very handy while solving the problems. Alright, I stop here. We'll meet on Thursday, 4 p.m.